Oh, hi, this is Mr. Gagnon again. This time we're going to look at a problem. It is a two-dimensional kinematics problem. Yes, we are going to call it the firing of a bullet. Okay? Firing of a bullet. All right. So we have a situation where we have a person here. Okay, and they are holding we'll call it a projectile launcher. Okay, we all know that it's a pistol. All right, so they're holding the pistol and they're aiming it horizontally. Okay, and this person is just doing a little target shooting, or in fact, they're missing the target. And we understand that when the person pulls the trigger, the bullet comes out, and it makes this this kind of path here, and then eventually hits the ground some distance away. Now we know that that gravity is pulling the bullet down, and we also know the rate at which gravity pulls the bullet down. Now, from the last video, the cliff video, we also know that the x velocity and the y velocity are completely independent of each other. So, it tells me a lot about this question. Okay, first of all, we want to know how far, what is the range of this projectile or this bullet or this, whatever you're going to call it. You can call it a slingshot, paintball, whatever you want to call it. We want to know how far this goes. Okay. Now, we know that the velocities of these things are pretty high. And we're going to apply a velocity in the x direction pretty high of that. Okay, with that. So, a story that was told to me when I was a kid, and I never believed it, was that if I took this hand, okay, and I took the bullet like this in my hand like this, and I just let it hit the ground the same time that I pull the trigger, that this bullet would hit the ground the same time this one would. And I never believed that as a kid. But now, after having taken some physics courses in college and such, I do realize now that everything falls at the same rate, no matter what its x velocity is. Just because this doesn't have an x velocity doesn't mean it's not going to fall at the same rate as this one. So that's a pretty cool concept to think about, because I can find out how long it takes for this bullet to hit the ground just by looking at how long this one would take to hit the ground. So the only thing I really need is how high this is falling from. And let's say it's like 2 meters. Okay, let's say we're falling from 2 meters. So the height is 2 meters. Can I put a negative sign because it is going to go down? I know that gravity, or acceleration of gravity, is negative 9.8 meters per second squared. And I can come up with a time that this thing's in the air for. Okay, so let's say we can find the time here. We know that a time of something in free fall is 2 times the displacement over acceleration of gravity, given no initial velocity. Okay, initial velocity would change it around a little bit. So to find the time that this is in the air for, it's the square root of 2 times negative 2 meters over negative 9.8 meters per second squared. So let's go ahead and figure this out. Okay. 4 over 9.8 So it's square root of 0.41, okay, equals 0.63 seconds. So this little guy here on this side of me dropping the object is going to take 0.63 seconds. Now this one on this side is going to also take 0.63 seconds to hit the ground. Now we can look at this a few different ways. Well, wow, this bullet will be way out here somewhere. In some cases, it's miles out. So that shows you how fast it's going in the x direction. So let's take a peek at it. Now we want to really find out how far, what's the range of the bullet at this height. So let's give a number of velocity in the y direction, initial velocity in the y direction, which by the way, x direction is equal to the final velocity in the x direction as well. So it's moving at the same velocity in the x direction this way. Okay. Now, yes, there's air resistance, guys, but we're using no air resistance here. So, so what we have here, let's say we apply a really large number to it, like 1,200 meters per second. So that means it's going 1,200 meters per second here, 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 and here. So it's moving that fast the entire trip in the x direction. Now, we have the time in the air, okay, because we know how long it takes to drop. So we're going to apply that to the x displacement. So x is vt plus half a t squared. We know in the x direction there is no acceleration. Get rid of that. Okay, so now we're left with x is vxt. Vx is vfx and v naught x. Same thing. And we can just apply some numbers here. So the velocity, okay, let's vxt. Wrote that twice. It's okay. 1,200 meters per second times 0.63 seconds. So this guy, when it hits the ground, is going to be, put it over here, 756 meters away. So almost a kilometer away. You got like 0.8 of a kilometer about. So that velocity stays the same, the x velocity, and its range, we call it, is 756 meters away. Because it's in the air for 6.63 seconds, it hits the ground. Now there's some questions as to the curvature of the Earth. So we have some people asking questions like, okay, the Earth has a curvature to it, so it does have a curvature. We do have a curvature problem, but that is negligible as well here. And I can actually get into some velocities where this keeps on going around the Earth, and that's something we call orbital velocity. So let's stop here, okay? And we've got the range of a we'll say a projectile launcher. We'll call it that, and maybe we can solve a couple more examples. Okay, have a great day.